So, we have found out the optimal separation LOPT between the buncher and catcher cavity. Let us now discuss the output power and efficiency that can be achieved in this type of two cavity klystron. As already mentioned, the maximum bunching should occur approximately midway between the catcher cavity grids. The phase of the catcher gap voltage must be maintained in such a way that the bunched electrons while passing through the grids encounter a retarding phase, so that they can transfer kinetic energy to the field of the catcher cavity. The fundamental component of the induced microwave current in the catcher cavity is given by I2 induced is equal to beta naught I2, which is beta naught 2 I naught j 1 x cos omega t 2 minus tau minus t 0. Here beta naught is the beam coupling coefficient of the catcher gap. If the buncher and catcher cavities are identical, then we will have beta I is equal to beta naught, and the magnitude of the fundamental component of current induced in the catcher cavity is I2 induced is equal to beta naught I2, which can be written as beta naught 2 I naught j 1 x. Now, this beta naught I2, this current actually flows through the parallel combination of these resistances R SHO representing the conductivity of the catcher cavity walls, RB is the beam loading resistance, usually very high, and RL is the load resistance that is connected to the output of the cavity, and this can be written as the combination of these three resistances can be represented by RSH, and V2 is the output voltage and beta naught I2 is the current that flows through RSH. Now, output power beta naught I2 square by 2 RSH, and which can also be written as beta naught I2 by 2 V2, and the electronic efficiency or the efficiency can be written as P out by P in. P out is beta naught I2 V2 by 2 and input power is I naught into V naught, and therefore, if we consider that beta naught equal to 1, perfect coupling, and the beam current I2 is such that it approaches its maximum value, which is given by 2 I naught into 0.582, and also V2 equal to V naught, then we can achieve the maximum efficiency. It should be noted that this is the maximum efficiency that we can achieve, which is approximately 58%. So, we have seen two cavity klystron, which is essentially an amplifier. We can have more than two cavities also. Let us now start a new topic, which is reflex klystron. A two cavity klystron amplifier with proper feedback arrangement can be operated as oscillator, but generally the reflex klystron is a single cavity klystron oscillator. It is a low power generator. The output of the order of 10 to 500 milliwatt in the frequency range of 1 to 25 gigahertz, and its electronics efficiency is of the order of 20 to 30%. This device is extensively used as a laboratory source for microwave measurement, in microwave receivers, as well as local oscillators in commercial, military and airborne Doppler radars. The schematic of the reflex klystron oscillator is shown here. We have a cathode which is heated, and the anode, it is maintained at a higher potential than cathode, and we can see that here the anode is at the ground potential, cathode is at lower potential as compared to anode, and there is only one cavity. So, this cavity does the function of bunching the electrons, as well as this is the cavity where the electrons also transfer their energy. In reflex klystron, we have a repeller which is maintained at a lower potential, and its job is to repel the electrons back to the cavity. Since it is an oscillator, it has only one output, but for the sake of explanation, we are assuming a small AC signal already present here. So, when the electron beams, when the electrons are emitted by the cathode, they travel, they are first accelerated by the anode, and then when they pass through the cavity grids, the RF signal present in the cavity produces velocity modulation of the electrons. These electrons then travel past the cavity, and finally the repeller repels them back, and they come to the cavity after travelling some distance. Now, here d is the distance between the grids, T0 is the time when an electron enters, T1 is the time when it leaves this cavity after being velocity modulated, and T2 is the time when the electrons comes back to the same cavity again after travelling certain distance. The separation between the cavity and the repeller is L. So, the electron beam injected from the cathode is first velocity modulated by the cavity gap voltage. All electrons are turned around by the repeller voltage, which then pass through the cavity gap in bunches, and that occur once per cycle. On their return journey, when the bunched electrons pass through the gap during the retarding phase of the alternating field, the electrons give up their kinetic energy to the electromagnetic energy of the field in the cavity, and the field within the cavity thus grows. The oscillator output energy is taken from the cavity. The electrons are finally collected by the walls of the cavity or other grounded metal part of the tube. So, here we are explaining, so an electron, here we are explaining how bunching occurs. So, an electron which was accelerated, which entered the cavity earlier and got accelerated, it travels a longer distance towards the repeller. Similarly, an electron which entered the cavity when the voltage, AC voltage is 0, its velocity remains unchanged and it travels a lesser distance and comes back to the cavity again. Similarly, the electron which was slowed down by the field in the cavity, this electron travels the least distance, and finally, if all the parameters are adjusted properly, after travelling certain distance, the electrons, they bunch at this point in the resonator gap, and at this instant, if the voltage, RF voltage in the cavity, it is such that it retards this electron, then they will deliver their kinetic energy to the field and the field will grow. Now, the round trip transit time in the repeller region can be given as capital T dash equal to T2 minus T1, and this can be found as 2 m L by E V r plus V naught. M is the electronic mass, E is the charge of the electron, and V r plus V naught is the total voltage multiplied by the velocity of the electron V T 1, and therefore, it can be written in this form: T dash is equal to T naught dash into 1 plus beta I V 1 by 2 V naught sin omega T 1 minus theta g by 2. We follow the same type of analysis as we have done in the case of 2 cavity klystron. And here T 0 dash is 2 m L V naught divided by E V r plus capital V naught. Now, the transit angle can be found out by multiplying T 2 minus T 1 by omega, and this can be written in the form of DC transit angle theta naught dash. It is the round the trip DC transit angle plus x dash sin omega T 1 minus theta g by 2. Here x dash is the bunching parameter of the reflex Klystron oscillator, and it is given by beta I V 1 divided by 2 V naught theta naught dash. So, having defined these parameters, we find that for a maximum energy transfer, the round the trip transit angle referring to the center of the bunch is given by omega T 2 minus T 1, it must be equal to omega T naught dash n minus 1 by 4 2 pi. We can see that here we showed the first bunching, which occurs as 3 T by 4. That means, which is this case is when n equal to 1. When n equal to 2, we will have 1 3 by 4 T. So, in general, we can write n minus 1/4 2 pi, and this can be written as 2 pi n minus pi by 2, and capital N is equal to n minus 1 by 4 is the mode of operation. The electronic efficiency of the reflex klystron, it can be calculated by finding out the AC power, and it is given by 2 x dash j 1 x dash divided by 2 pi n minus pi by 2. Now, we are not going into the detailed derivation of this for reflex klystron. In practice, the mode of n equal to 2 or 1/3/4 mode, it has the most output power, and we also find that this quantity x dash j 1 x dash, it reaches its maximum value of 1.25 at x dash equal to 2.408, and once we substitute n equal to 2 here, x dash J1 x dash equal to 1.25, then we get the maximum efficiency to be 22.7%. In the beginning of this discussion, we have mentioned that reflex klystron has efficiency ranging between 20 to 30%. So, we get a value of 22.7%. Depending upon the adjustment of the repeller voltage, we can see that if the repeller voltage is very high, the electrons will be sent back to the cathode after travelling short distance, whereas when the repeller voltage is low, the electrons can move for further distance towards the repeller, and therefore, based on this setting of the repeller voltage, we can have different modes. The mode one with the highest power we have already mentioned is 1/3/4 mode, and these modes will have different amount of power. Usually, as the value of n increases, we get lower power. Also, the frequency around the resonant frequency f naught, where this power is available, is indicated, and these are only some representative plots showing the behavior of the device. So, we have discussed the basics of reflex klystron, how it operates, the efficiency that is achieved. Next, we move on to another topic, magnetron. A magnetron is a cross field device, and it has both DC magnetic and electric fields which are applied to the device perpendicular to each other. The mechanism of generation of microwaves in a magnetron involves interaction of electromagnetic fields with electrons moving in such cross fields. The mechanism of generation of microwaves in a magnetron involves interaction of electromagnetic fields with electrons moving in such cross fields. Various types of magnetrons have been developed. Here, our discussion will be limited to basic cylindrical magnetron. Now, a magnetron is an oscillator, and it can generate both continuous wave or pulsed power. Generally, the peak power that can be generated by these magnetrons are very high, may go several megawatts, but that power will exist only for a short duration. In a pulsed magnetron, the average power will be of the order of few hundred of kilowatts. As we have said, we will discuss the basic magnetron, a cylindrical magnetron, and the cross section of such magnetron is shown. Here we have a cathode surrounded by an anode block, where we have cylindrical cavities. Now, between anode and cathode is the interaction space. These cavities, as we can see, has opening to the interaction space. So, the electrons emitted by the cathode will be accelerated by the field present between cathode and anode, and also a magnetic field perpendicular to this electric field is applied along the axis of the magnetron. Finally, the RF output is taken out. Here a loop coupling has been shown, and since this type of device, these are evacuated devices, we need to connect this device to rest of the circuitry operating under normal atmospheric condition through an RF window, which acts as a barrier between this vacuum and the normal atmosphere outside the window. We have shown the cross section of a hole and slot magnetron. The anode cavities, different types of anode cavities are used, like rising sun, simple slot, vein. Let us now discuss some basics about the motion in cylindrical coordinates, the governing equations. Because we are dealing with the cylindrical magnetron and an electron is subjected to electric and magnetic force because of the field present. So, how we describe the motion in terms of the mathematical equations, these basics let us discuss. The velocity in cylindrical coordinate, we can write dr dt, ur is the unit vector along r, then r d phi dt, u phi is the unit vector along phi, and dz dt, uz is the unit vector along z. We are using a cylindrical coordinate r, phi and z. Now, the acceleration, which is time derivative of velocity, it can be written in this form. Again, it is shown as its r, phi and z components. Now, if an electron is placed in an electric field, then it will experience a force of minus E, electric field E, and this can be written as mass into acceleration. So, from the expressions we have given for acceleration, we can now write, we can equate component wise. So, the r component of the field and r component of acceleration, we can write d square r by dt square minus r d phi dt whole square is equal to, from here, minus E by m and ER component. Similarly, we can write for E phi and Ez component. When an electron, it moves with a velocity v in a magnetic field, the force that acts on it is given by minus E v bar cross v bar, and that can be written as now m a, and once again using the relation given for A, we can write so we have these sets of equations. Please note that in our case, in the cylindrical magnetron, we are applying only ER, and also we are applying only BZ. So, these two components, the equations which contain ER and BZ, those two equations will be useful to us. And we also define cyclotron angular frequency of circular motion of the electron. Now, because V and F, these two are perpendicular to each other. This force, it is perpendicular to both V and B. So, this force being a perpendicular force will try to move the electron in a circular path. So, the electron trajectory, it will change into a circular path, and cyclotron angular frequency of the circular motion of the electron, it is given by omega is equal to V by R is equal to EB by m radian per second. Now, this R we obtain from the fact that mv square by R must be the centrifugal force of the electrons must be balanced by E V B, the force produced by the magnetic field, and from this we find that V by R is equal to E B by m, and this V by R is the cyclotron angular frequency omega. Now, having discussed these basics, we can now move on to study the electron motion under combined magnetic field. So, in our magnetron, we have both electric field, applied electric field which is radial, and applied magnetic field which is along the axis. So, an electron will move under the influence of both the fields. When the DC voltage and magnetic flux are adjusted properly, the electrons will follow cycloidal path in the cathode anode space under the combined force of both electric and magnetic fields as shown. So, when no magnetic field is there, since we have a anode is at higher potential, we have the electric field E. So, the electrons will be emitted by the cathode, will be accelerated by the anode and it will move towards the anode. As we apply this magnetic field B, now the electrons will experience a sideway force and its path will change from this linear towards circular as we keep on increasing B, and if B is increased beyond certain value, the curvature of this path will be such that the electron, instead of reaching anode, it will come back to the cathode. So, we see that for a given electric field, we will have a magnetic field for which the electrons will be coming back to the cathode instead of going to anode. Now, the motion under combined electric and magnetic field, it is given by F is equal to sum of the two forces. So, minus E plus V cross B, and this can now be written as m dV dt. So, from our previous discussion, we can write d square r by dt square minus r d phi dt square. This now becomes E by m here. Please note that our E is from anode to cathode. So, this minus sign is not there as we saw in the earlier case, minus B z r d phi dt, and one by r d dt of r square d phi dt is equal to E by m B z dr dt. So, these two equations actually come from the discussion we did earlier separately for electric field and magnetic field. Now, we need to combine these terms so as to take into account the combined force that an electron experiences. So, this is the same set of equations. So, from these two equations we can write d dt of r square d phi dt is equal to E by m B z r dr dt. Now, r dr dt we can write half d dt of r square, and E B z by m we can write omega c, the cyclotron frequency. Integrating the above equation, we get r square d phi dt is equal to half omega c r square plus some constant of integration. Now, at r is equal to a, where a is the cathode radius, we should have d phi dt is equal to 0. The phi component of the velocity is 0, and therefore, if we put d phi dt equal to 0, the constant evaluates as minus half omega s square. So, when this constant is substituted and then we divide by r square, we get d phi dt is equal to half omega c 1 minus s square by r square. Since the magnetic field does not work on the electrons, because the force is always perpendicular to the motion of the electron, the kinetic energy of the electron, it is given by half mv square, and that can be equated to ev. However, the electron velocity has r and phi components, and therefore, we can write v square is equal to 2 E by m v, and that can be written as v r square, r component of the velocity square, plus phi component of the velocity square, and r component of the velocity is given by dr by dt, and phi component of the velocity is given by r d phi dt. Now, at r equal to b, where b represents the anode radius, we have potential V equal to V naught, and also if we have dr dt equal to 0, then the electrons will just graze the anode. So, if we put these conditions, then we get b square d phi dt d phi by dt square is equal to, because dr dt we are putting 0, 2 E by m, and this V becomes V naught, and therefore, we get d phi dt is equal to half omega c. We have also seen d phi dt is equal to half omega c 1 minus s square by b square, and therefore, now we can substitute this d phi dt here by this expression. So, once we make this substitution, we get b square half omega c 1 minus s square by b square whole square is equal to 2 E by m V naught. So, this equation, it is the Hall cutoff magnetic equation, and from here we can, for a given V naught, we can find out the cutoff magnetic field BOC. So, this BOC we can get by substituting omega c is equal to E B OC by m, and then we rearrange the terms, we get the Hall cutoff magnetic field, and if B naught is greater than BOC, the applied magnetic field is greater than this cutoff magnetic field for the given V naught, the electrons will not reach the anode, because we have derived this condition considering that dr dt becomes 0 at the anode. Alternatively, we can, given B, we can find a cutoff voltage. So, VOC is the cutoff voltage for a given V naught, and if applied voltage V naught is less than VOC for a given V naught, electrons will not reach the anode, and this is called Hall cutoff voltage equation. So, these two voltage equations, the cutoff magnetic field equation and cutoff voltage equation, they are very important, because they determine what should be the applied magnetic field, so that the electrons do not reach the anode, or what should be the applied V naught for a given B naught, so that the electrons will not reach the anode. Now, we qualitatively discuss the very important mode of operation of magnetron, which is called pi mode. So, a magnetron has number of cylindrical cavities opening in the annular region between cathode and anode, which is called the interaction region, and pi mode is the mode where the phase shift between the fields in the adjacent cavities is pi radian. We will see why it is important, and for practical magnetron, the frequency of this mode is easily separated from adjacent mode by incorporating conducting straps connected to alternate segments of the anode block. So, it is very easy to separate out this particular mode from the other adjacent modes. Now, qualitatively, let us see how the electrons they transfer energy to the cavities when operating under pi mode. Suppose as we have seen that the voltage, when it is below, the voltage and the fields, magnetic fields, they can be set up in such a way so as to decide whether an electron will reach anode or it will come back. Suppose for the time being, let us assume that there is no RF field present in these cavities, and the DC fields have been set in such a way that this electron, which is denoted by anode, it is emitted and it is repelled back to the cathode. Now, in the presence of this RF field, and if the field configuration is favorable, that means here we can see that the electric field component, they are actually in the same direction as the velocity of the electron here. So, what will happen here, the electron will get retardated, and as a result its radius will increase, and this electron in the presence of this RF field, instead of following this path, its trajectory will be what is shown as A with larger radius of curvature, and this field being a retarding field, it will actually extract energy from the electron and its radius of curvature will increase further. Now, if the adjustments are made in such a way, by the time this electron marked A travelling along this trajectory comes to the second cavity, when this field now changes, because we are talking of pi mode. So, there is a phase shift of pi, you can see in the field. Now, by the time the electron travels to the second cavity, its field polarity changes. In that case, it will further retard the electron, and this field also will extract energy from the electron, and eventually the electron will get collected at the anode. So, these are the electrons which will contribute to the building up of field in the cavity. Let us now consider another case. When this electron was emitted here, correspondingly another electron B naught, whose trajectory is shown in the absence of RF field, but because of this RF field present and this field is now opposite to the direction of movement of the electron, it will reduce the radius of curvature, and instead of following B naught path, it will follow this trajectory B and come back to the cathode. So, we see that, but in that process this electron following this trajectory B, instead of delivering energy to the field, will extract energy from the field. So, we see that we have both type of electrons, the electrons which delivers energy to the field and electrons which extract energy from the field. Now, this type of electrons following this trajectory B, they are quickly removed from the interaction space, whereas the electrons following the trajectory A, they remain for a much longer time in this interaction space, and they visit multiple cavities, and therefore, they deliver more energy than what is extracted by these electrons shown by the trajectory B, and as a result overall the oscillation grows. So, qualitatively this is how in a magnetron the oscillation can grow, and finally a steady state is reached and power can be extracted from the magnetron using appropriate arrangement as discussed earlier. So, with this we come to the end of our discussion on magnetron. Next we will discuss travelling wave tube. We have seen the working of different microwave tubes such as Klystron, Reflex Klystron and magnetron. Let us now consider another microwave tube which is known as travelling wave tube, or in short TWT. We will discuss only the basic operation of such tubes without going into much mathematical details. In TWT or travelling wave tube, the microwave circuit is non-resonant. So, we have seen in the case of klystron or magnetron, we had resonators. Here the microwave circuit is non-resonant and the wave propagates with the same speed as the electrons in the beam. A slow wave structure is used to slow down the wave. A small amount of velocity modulation is caused by the weak electric fields associated with the travelling wave. This velocity modulation later translates to current modulation, which then induces an RF current in the circuit, causing amplification. So, we have this slow wave structure where we have a signal is given at the input, and then as this wave propagates down the slow wave structure, it interacts with the electron beam and that results into amplification of the signal, provided certain conditions are met. The interaction of electron beam and the RF field in the TWT is continuous over the entire length of the circuit. This is in contrast to say klystron, where we had the interaction of the field and the electrons for a very brief period when the electrons pass through the buncher or catcher cavity. So, in a TWT this interaction is continuous, and as we have mentioned, the wave in a TWT is a propagating wave, whereas in klystrons or magnetron the wave remains confined within the cavities. A helix travelling wave tube consists of an electron beam and a slow wave structure. Now, TWTs also come in different forms. We will discuss the basic TWT configuration, which is a helix TWT, the electron beam is kept focused by a constant magnetic field along the electron beam and the slow wave structure. So, we have a slow wave structure which is helical structure, and an axial magnetic field is applied to keep the electron beam focused. So, the very basic structure of a helix TWT is shown. So, it has a cathode which emits electrons. We are not showing the biasing arrangements here. The anode accelerates the electron, and then this beam of electron, they enter the slow wave structure, and RF input is provided here, which sets up the wave in this slow wave structure, and these electrons, when traveling within the interaction space, they interact with the wave in the slow wave structure, and this interaction is continuous. The bunching of electron takes place due to velocity modulation, and when bunching of electron take place, it results into current modulation, and finally, the RF input is amplified by exchange of energy from the electron beam, and the electrons, after leaving the interaction space, are collected by the collector. Here we see the magnetic focusing structure which applies a field so that the beam remains focused. The applied signal propagates around the turns of the helix and produce an electric field at the center of the helix, which is directed along the helix axis. When the electrons enter the helix tube, an interaction takes place between the moving axial electric field and the moving electrons. On the average, the electrons transfer energy to the wave on the helix. This interaction causes the signal wave on the helix to become larger, and this is how we get amplification of the signal. Those electrons which enter the helix at 0 field are not affected by the signal wave. Those electrons entering the helix at the accelerating field are accelerated, and those entering the retarding field are deaccelerated. As the electrons travel further along the helix, they bunch at the collector end, and bunching shifts the phase by pi by 2. The electrons in the bunch encounter a stronger retarding field. Microwave energy of the electrons is delivered by the electron bunch to the wave on the helix. So, here we briefly discuss the slow wave structure we have shown an helical structure. So, this distance between these turns, it is the pitch p of the helix, and d is the diameter of the helix, and we can see that pi d, we can find out actually pi d is the distance that is travelled from this end to this end, and p is the pitch. So, we can write that the actual distance is under root p square plus pi d square. Here this angle psi is the pitch angle. Now, this helix structure may also be in a dielectric field cylinder. In that case, we get the phase velocity V p epsilon is equal to p by root mu epsilon p square plus pi d square. For a very small pitch angle, the phase velocity along the coil in free space is approximately represented by V p is equal to P c divided by pi d, and this is omega by beta. Here we can see that when mu is equal to mu naught, epsilon equal to epsilon naught, and p square, it is neglected with respect to pi d, then we have V p epsilon, we have V p is C p divided by root pi d square. So, it becomes C p by pi d. So, this is the velocity in the axial direction. In the helical slow wave structure, a translation back or forth through a distance of one pitch length results in an identical structure, and thus the period of a helical slow wave structure is its pitch. The characteristics of the travelling wave tubes are: it is usually operated in the frequency range 3 gigahertz and higher. Bandwidth is about 0.8 gigahertz. So, this is a huge bandwidth. Efficiency 20 to 40%, and power output up to 10 kilowatt average, and power gain up to 60 dB. So, TWT is often used as amplifiers in different systems such as radar, communication satellites, and many other broadband applications. So, in this module, we have seen some basics of some of the commonly used microwave tubes. We discussed the limitations of conventional tubes in the microwave frequency range, and then we have seen how these limitations are overcome in specially designed tubes such as klystron, magnetron, and finally in TWT. It may be mentioned that when it comes to very high power microwave application, the tubes are extensively used as microwave signal source or for amplification purposes. In the next module, we will introduce devices based on ferrites. We will first discuss the basic properties of ferrites, briefly discuss the wave propagation on ferrites, and then we will discuss two very important devices, isolator and circulator, which are designed using ferrites.